Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class, we had started to discuss about route choice in the case of stochastic network loading mechanism. So, today we will be continuing in that direction. So, suppose if the population of drivers between origin R to destination S is large, the share of drivers that will be choosing the kth route is given by this probability PKRS. Okay. So, this is equal to the probability that the perceived travel time on the kth path is less than or equal to the perceived travel time on all the other paths. Okay. So, in other words, the probability that a given route is chosen is the probability that its travel time is perceived to be the lowest among all the alternative routes. Okay. So, this above equation specified a route choice probability that can be interpreted in the framework of discrete choice models. Okay. So, if you remember, we had said that we will be assuming that every perceived travel time between a given path from origin R to destination S will be having a distribution. Okay. So, now the question is that if suppose there are two paths, we say that suppose the first path has travel time that lies in this distribution, the second path has travel time that lies in this distribution. So, now we cannot say for sure that the travel time on this path will always be less than or equal to travel time on the other path, because these are two distributions here. So, depending upon which value you pick from these two distributions, then we will be able to say that which one is lower on and which one is larger. Okay. But what we can say here is that what is the probability that if you pick a given value from this distribution of the travel time of the first path, then what is the probability that it will be less than or equal to the value that you pick from the second distribution. Okay. So, that is why we can actually determine the probability of choosing different routes given that we have these distributions of travel time given to us. Okay. So, in this step I would like to emphasize that we are assuming that the path travel times are not function of flow. So, this dependence of the travel times on the flow will be encountered later. Okay. So, right now we are in that framework that the travel times are stochastic across different paths, but they are not varying with flow. So, in that case, how do people distribute themselves across different origin destination pairs? Okay. So, I would like to again emphasize is that all of this discussion is being closely followed from this reference of urban transportation networks by Joseph Sheffy. So, interested readers can also check that reference. So, the population of interest between any origin R to destination S is equal to the trip rate or the travel demand, that is QRS that we had been using. So, each alternative path is having some utility function UKRS. Okay. Now, the utility of each alternative path equals to the negative path cost. Okay. That is, we are assuming that the utility of choosing the kth path from origin R to destination S is equal to minus of the perceived travel time on this path K connecting R to S. Okay. Why we are doing that? Because first thing is that we are assuming that the utility of choosing any path is only a function of the travel time. Okay. So, that is why there are no other attributes or factors that are being considered. And the other aspect is that the way we had discussed about discrete choice models in a few lectures back, the alternative that has higher utility is considered to be better, that is, it has higher likelihood of being chosen. Okay. Now, in the case of route choice, the route that will be experiencing lower travel time should have higher probability of getting chosen. Okay. So, therefore, the utility should be negatively be proportional to the travel time. Okay. So, that is why we are saying that the perceived utility of choosing the kth path from R to S is equal to negative of the perceived travel time from path K connecting R to S. Okay. Okay. So, various models of stochastic network loading differ from each other in the assumed distribution of the perceived travel times. Okay. So, this is along the same line saying that different discrete choice models differ in terms of what assumption that they make in terms of the error distribution. Okay. And since those error distributions govern the distributions of the perceived utilities, so that is why in that same way um, what is the distribution of the perceived travel times will be affecting what kind of stochastic network loading model that we have. Okay. So once this distribution is specified, the probability of selecting each alternative route can be calculated and the flow can be assigned accordingly. Okay. So once we know that what is the, for example, the distribution that governs the perceived travel time on pathway connecting R to S. Okay, so then we can calculate, for example, this probability, that what is the probability that this perceived travel time on pathway connecting R to S is less than or equal to the perceived travel time on all the other paths which are connecting uh, this path, this origin R to destination S. Okay, so what is the probability of that? Okay, so this is equal to PKRS. Okay, so once we have the distribution of this and the distribution of this, we can actually determine this probability. Okay, and once we know this, then we can multiply this with the total demand that wants to travel from origin R to destination S to determine the flow on pathway connecting R to S. Okay. So this is the same thing saying that, for example, if there are 100 people who want to travel from A to B, and suppose the probability that the perceived travel time on the first path is less than the perceived travel time on the second path is suppose 0.4. So then 40 people will be actually choosing the first path and 60 people will be choosing the second path. Okay. And this calculation of 40-60 will be more exact if the total number of people who want to travel from A to B is large. For example, rather than having say 100 people, if it was 1 million, then this assignment that 40% of that will be traveling the first path and 60% of that will be traveling the second path will be more exact, because population that wants to travel, the more will be the error associated with this. Okay. So once we have determined the path flows on different paths connecting R to S, then we can determine the link flows. Okay, using this link path incidence relationships. So this we have seen many times before in the constraints of user equilibrium system optimization. So one of the practical reasons for using stochastic network loading is the sensitivity of the flows in deterministic models to small changes in the network is very high. Okay. So let us consider an example to understand this. Suppose there is one origin to destination and suppose it is connected by two routes. Okay. Now according to a deterministic network loading model, all or nothing assignment, all the flow from origin to destination, suppose that total flow is Q, will be assigned to the lowest travel time path. Okay. So we have seen this before, that all the flow from O to D will be assigned to that path that has the lowest travel time. Okay. Suppose Q is that total flow. So whichever route has the lowest flow, we assign all the flow to that. Okay. So suppose the travel time on the first path, now this is the measured travel time, that is why it is C1, is equal to C2 plus delta t. Okay, so this is the deterministic case. So the measured travel time on path is the same as the perceived travel time. So here we are saying that the travel time on the first path is greater than the travel time on the second path by this difference delta t. Okay. Now if that is the case and we are doing this deterministic network loading, that is we are doing all or nothing assignment, so then we will be assigning all the flow to the path that has the shortest travel time. Now in this case, given that delta t is positive, so path 1 has larger travel time and then path 2 because of this relationship. Okay. So therefore all the flow will be traveling to the second path and the flow to the first path will be equal to 0. Okay. And this will be true for any value for of delta t, as long as this delta t is greater than 0. It does not matter how small is delta t. Okay, whether this delta t is 0.1 or whether it is say 0.0001. So the only thing that will be mattering here is that this travel time on the first path will become larger than the travel time on the first path, and therefore second path, and therefore the all the flow will be assigned to the second path here. Okay. Now note that each path in this network, however, may include various transportation facilities such as bridges, intersections, etc. Okay. So a small error in the data measurement of any one of these facilities may cause C1 to be lesser than C2 by a small amount. Okay. So the C1 and C2 are the measure or the actual travel times. Now there can be some issues in terms of the measurement of the travel time across different paths. Okay. Now if this C1 and C2 are actually very close in the real world, then it can, for example, sometimes happen that C1 might be captured to be slightly lower than C2. Okay. Now as soon as that happens, all the flow will then be assigned to the first path. Okay. And zero flow will be assigned to the second path. So this is what it is saying, that such a change, however, mean that the calculated flow pattern over the network will be very different, with the first path getting all the flow and the second path getting zero flow. Okay. So we see that if the travel times are very close for different paths, okay, so it can happen that if we are using deterministic network loading model, if there is small sensitivity in the calculation of the travel times, that is, sometimes, for example, if C1 becomes less than C2, then all the flow is assigned to the first path, whereas the reverse happen that C2 is less than C1, then all the flow gets assigned to the second path. So this fluctuation of the flow can happen significantly if the travel times are very close. Okay. But the stochastic network loading models usually avoid such sensitivities. Okay, that is why they are much more useful, and they are more general than the deterministic network loading models. So note that the probability that route 1 will be chosen will be approximately 0.5 if the major travel times of the first and the second path are almost equal. Okay. And therefore a small change in the travel time will result in very small change in the flow pattern. Okay. So regardless of whether C1 is just slightly less than C2, then we might be experiencing that maybe the probability of choosing the first path is 0.51. Whereas if C2 is just slightly less than C1, then probability of choosing the second path might be 0.51. Okay. But you can see that the probability of choosing any given path here just changes from 0.51 to 0.49. Okay. But that fluctuation is not that high as compared to when we are using the deterministic network loading model, where the whole flow can actually shift from one path to the other when these path travel times are very close. Okay. So these sensitivities are not there when we are focusing on stochastic network loading models. Okay. So the exact magnitude of the change in the flow will depend on the variance of the distribution of the path travel times. So here in this figure we have the probability of choosing the first path on the y-axis, and we have C2 minus C1, that is the travel time on the second path minus the travel time on the first path here. These are the measured values that we have, and you see that there are three curves here. So this value is denoting probability of 1, and this is denoting probability of 0. Now here the three curves correspond to different variance that are associated with the perceived travel times. So this is what it is saying. The shown figure demonstrates the effect of the travel time distribution variance on the flow pattern for the simple two-link network considered here. Okay. So it describes the choice probability of route 1 P1 as a function of the difference among the routes measured travel time C2 minus C1 for various values of the travel time variance. Okay. So it is giving what is the probability of choosing the first route as a function of C2 minus C1 depending upon what is the level of the variance across the travel times. One thing which is actually the same across all of these three curves, whether it is this low variance curve, or whether it is this intermediate variance curve, or whether this is this large variance curve, is that uh, an increase in P1 is there as C2 minus C1 increases. Okay, so P1 will increase if C2 minus C1 increases, and that is also expected because as the travel time on the first path becomes smaller as compared to the travel time on the second path, so the probability of choosing the first path should increase. Okay, now what we see here is that for very low variance, that is this curve here, this one, this one, the curve is very steep, meaning that the travelers perceive the differences between C1 and C2 accurately and act accordingly. Okay. Now, in fact, if the variance is 0, then this corresponds to the case of deterministic case, that is, as soon as C2 will become less than C1, then the probability of choosing the first path will become equal to 0. Whereas as soon as C1 becomes less than C2, the probability of choosing the first path will become equal to 1. Okay, so you see that there is a sudden shift from here directly to here when we have this low variance case. Okay, so this low variance case in the limit when the variance is 0 becomes equal to the deterministic case, and that's what I've been saying, that when there is no variance, that is there is no stochasticity, then these models become equivalent to the deterministic case. Okay, so this kind of assignment is the same as the all or nothing assignment, that is all the flow goes to the path that has the lowest travel time. So that is what it is saying, that this route choice behavior is associated with the deterministic model where the driver's perception of travel times is assumed to be perfectly accurate, and therefore there is zero variance that is associated with the travel times. Okay. So at the limit when the variance is extremely large, the actual travel times do not affect the perception, which is completely random. Okay. Now we are considering the other extreme case here, when there is very large variance. Okay, so when that is the case, the actual travel times will not affect the perception. Now in this case, the probability of choosing both the paths is 0.5. This is the case we are talking about. Okay, so now it is as likely as to pick one path as compared to the other. Okay, because there is just so high variance, I mean. Okay, now this case is corresponding to the case, this straight line, when the variance goes to infinity. Now in the real world, that will not be the case, it will be some finite value, so this is the limiting case. Okay, so in this case it is being said this probability of choosing the first path is 0.5, and also the probability of choosing the second path is also 0.5 for any value of C2 minus C1. Okay, so therefore the actual magnitude of the perception variance should be determined empirically on a case to case basis. Okay, so now the question is that which curve should be followed in the real world. So for that we need to have some idea of the perception variance across the travel times. Okay, and that can only be determined empirically, that is some maybe survey has to be done among the set of travelers that we have, and then only we can get an idea of that whether this perception variance is high or low. Okay, and depending on that we can choose the appropriate curve here. Okay, so these route choice models can be perceived as discrete choice models. In the utility of traveling over a given path, UKRS is given by UKRS being equal to minus theta CKRS, where theta is a positive unit scaling parameter. Okay, so if you remember, we had previously said that UKRS is suppose equal to minus CKRS. Okay, but now we have put this scaling parameter also here, theta. Okay, so this is important because the utility of choosing the kth alternative will actually determine what is the probability of choosing that. Okay. Now, the probability of choosing any given path as compared to the other should not change if the units that we use to measure the travel times vary. For example, if I say that suppose uh, the distribution of the travel time of the first path is being specified in terms of meters, okay, and similarly for the second path also. Now, whether you specify these two distribution in terms of meters or kilometers, the probability of choosing each of these paths should stay the same, right? It should not change. So therefore, in order to take that into account, we don't want that this UKRS change if the units of CKRS change, whether this is specified in meter, kilometer, should not affect UKRS, because if that changes, then the probability of choosing different paths also change, which is not realistic in the real world. Okay. Also, the satisfaction function for a model of choice between alternative paths connecting OD pair RS is given by this here. Okay. So, this is saying that we are taking the max over all the routes k that are there among the set of all the paths. Okay. So these route choice models focus on travel time minimization rather than utility maximization. Okay. So therefore, we are also defining this SRS, which is also a function of the measured travel times, like in the same way the satisfaction function was the function of the measured travel times. So this is the expected perceived travel time between origin R and destination S. So this satisfaction function that we had seen in the last class was the expected utility of choosing a given path between origin R and destination S, and this one is the expected perceived travel time from origin R and destination S. Okay. So the mathematical expression for this is given as this here. So this is equal to the expected value of the min of this CKRS here. Okay. So since we are taking the expected perceived travel time here, so that's why instead of UKRS there is CKRS here. And since the path that has lower perceived travel time will be considered to be better, that's why we are picking the min here. It's not a max operator here. Okay. So this will give us the expected perceived travel time between origin R and destination S. Now there is a relationship between this expected perceived travel time function and the satisfaction function, which gives the expected utility. Okay. So this can be obtained by substituting this perceived travel time on path K connecting R to S to be equal to minus 1 by theta times UKRS. Okay. So that is what we are going to do here. So in this expression, we will be replacing CKRS with this expression here. Now we can take out minus 1 by theta outside, and when we do that, this is what we will be getting. Okay, so the min operator will be turning to max here. Okay, so now this expected value of the maximum utility, so this is equal to the satisfaction function that we had defined before. Okay, so in this way we have connected this expected perceived travel time between origin R and destination S to the satisfaction function that we have. Okay, so they are connected by this parameter here minus 1 by theta. So we are just writing this here again. So the expected perceived travel time function is minus the satisfaction function scaled in terms of the travel time units. Okay, so why we are saying scaled in terms of the travel time units, because we have this minus 1 by theta here. Okay, so this captures the expected disutility of travel between origin R to destination S, okay, as measured in travel time units and as perceived by a randomly selected motorist. Okay. Now, the total expected perceived travel time between OD pair RS is what? It is QRS times this SRS. SRS is the expected perceived travel time between R to S. So, the total expected perceived travel time will be obtained by multiplying the travel demand from R to S. Okay. Note that the properties of the expected perceived travel time are similar to those of the satisfaction function except for its orientation towards travel time minimization rather than the utility maximization. Okay. So, note that the first difference is that this SRS is concave with respect to CRS. Okay. That is, this expected perceived travel time is concave with respect to the measured travel times. Okay. Furthermore, as with the satisfaction function, the marginal expected perceived travel time of OD pair RS with respect to CKRS is the probability of choosing that route. Okay. So, this is what we get. So, if you take the derivative of this function with respect to CKRS, then we will be getting the probability of choosing this kth alternative. Okay. Where PKRS is the probability that the travel time on path K between R to S is smaller than the travel time on any other path. Okay. Actually, this is the perceived travel time. Okay. And the final property is that this SRS, that is the expected perceived travel time, is monotonic with respect to the number of available paths between R to S. Okay. So, this is the property. Now, the only difference is that you see that this is less than or equal to. So, when we add one more path L here, which is not in this set already connecting R to S, then this expected perceived travel time can be equal or less as compared to before. So, this is what it is saying, where the vector of paths times CRS does not include the measured travel time on path L. Okay. So, now we will be moving towards Logit based loading. So, we have seen that there are different kind of discrete choice models. The question is that, for example, if you have to use this multinomial Logit models, how we can use it in this network loading. So, the utility of choosing the kth path between origin R and destination S is UKRS. Okay. So, it is given by this here. Okay. So, if you remember, another connection that we had seen is that the utility of choosing the kth path from R to S is minus theta times this perceived travel time on path K connecting R to S. Okay. And we know that this CKRS is equal to this perceived travel time on path K connecting R to S is equal to the measured travel time. This is small c. Okay, this is small c connecting R to S plus this error term here. Okay. Notice that this error term is not the same as this. Okay. So, here in this equation here CKRS is the measured travel time, theta is a positive parameter here, and this error term is a random term with distribution given by Gumbel density function. Okay. So, if you remember, in the Logit choice model, we had assumed that the error terms are IID Gumbel variates, that is, they are independent and identically distributed Gumbel variates. Okay. So, this error term, which is actually coming in the calculation of the perceived utility of kth path connecting R to S. So, this is actually a random term given by Gumbel distribution, not this one actually. Okay. But this and this error term are connected. So, we will be seeing how that is the case. So, that is very easy. So, this random variable EKRS is related to the random term in the perceived route travel time mentioned in the last lecture by this thing here. Okay, so this can be obtained from the relationships that I showed in the last slide. Okay, so this I'll leave it as an exercise for you. Okay. So since these error terms associated with all the paths are assumed to be identically distributed, this error term can be replaced by this. That is, since each of these error terms are assumed to be independently distributed Gumbel variates, so the distributions of all of these error terms are same, even though these error terms are having independent distributions. Okay, so that's why we can replace each of these error term by this. Okay, but that does not mean that these error terms will always take the same values across all the different paths. Okay, so for example, if suppose there are two alternatives and you have to pick the error term values for that, so we'll be randomly picking one of the values from this distribution for the first path, and for the second path again we'll be randomly picking this value from the same distribution, but that does not mean that these two values that have come out are the same. Okay, so that is important to remember. Okay, so with this we'll be pausing the discussion here and we'll be continuing the discussion in the next class. Thank you.